Alright guys, let's talk about some factors that affect the rate of reaction, okay? Some reaction conditions that can change the steepness of the curve in that graph, okay? So, just briefly, temperature, concentration, surface area, mixing, and catalysts. We're going to consider each in their own time. Okay, let's do temperature first. So temperature down on the molecular and atomic scale is kinetic energy, okay? So molecules can move through space, which we call translational motion. Okay, here in the diagram on the right. So movement through space. And they can do all these other things too to express temperature. So we've got vibrational motion, which here is like stretching and bending. And you've also got twisting and turning in there as well. Okay, so not just moving through three-dimensional space, all these other ones too, okay? The lower the temperature, the lower the amount of these motions, okay? Or the slower they are. Increase the temperature and you get more of these, so more bending, more stretching, more rotation, more translation, okay? So, gaseous state has all three of these motions, okay? That you remember from our particle model that gaseous particles can move freely in three dimensions and at speed. So they've got translational motion. They can also spin and rotate, and they can also bend and stretch. Okay, they're very free. There's no attractions to there. Let's take it down to liquids. So remember our particle model for liquids, the particles are packed together, but they can freely move around each other. Okay, so they can definitely do the stretching and bending within the molecule. The rotation, no, it's getting a bit smaller. Okay, you've got stronger attractions, you've got less of that rotational motion. Okay, and translational motion is very small. Okay, they've got to stay next to each other, the particles, so they can move, but they must move in a way that they're sticking together. Okay, for a solid, we've got stretching and bending in place in its rigid three-dimensional matrix structure, but we don't have rotational motion really, okay? They're rigid, they're tightly held with those intermolecular forces or those ionic bonding kind of forces. So no rotational motion and no translational motion, okay? It's sticking to its matrix, its three-dimensional matrix, okay? Let's keep going. We've got an aqueous solution. You've got bending and stretching, of course, as well. Rotational motion, yeah, they're more freer. You can have a medium one like a liquid. Still, you've got water particles surrounding whatever it is in aqueous solution, so it's kind of inhibiting it a bit and attracting it. But so slow rotational motions, and the translational motion is also much smaller. It can move a little bit over time, but it collides with water particles, so it's kind of got an edge around them, just like in a liquid, so small again. So temperature has a function of changing these conditions, okay? And when we're talking about the speed of reaction, we're mainly talking about the translational motion. That's the most important. So let's draw a big pink box around this. When we're talking about temperature and effect on it, we're talking about the ability for successful collisions. So it's really just down to translational energy. And you can see that liquid and aqueous have small, solids not at all, and gases have a lot of translational energy. So that's another way to think about why you get different rates of reaction for different states, because of that difference in translational motion. Okay, one thing to note here is that all molecules, especially molecules in a gas, but all molecules do not have the exact same kinetic energy. There's a range of kinetic energies. So say you have a canister of CO2, they will have roughly the same energy, but they will have like a bell curve of energies. There'll be a small amount that has much lower, there'll be a small amount that has much higher than an average, but most will be around an average. So it forms like a bell curve of translational energy or speed and the number of molecules. So most molecules will have a rough number there, like an average. A small will have a small amount and a small will have a large amount. So there's a good video here that I've linked link to. I'll put a GIF in there as well. It'll help if these little robots were moving, but you can see that here they're using temperature to color to express temperature. So this is a cold one where most are blue but a little hotter, and here's a hot one where most are kind of red but a bit cooler. Okay, and so what happens is when you heat up or you increase the temperature of these particles, what you're doing is broadening this curve. You're always going to get a curve though. So you can see here we've got particle speed versus basically the amount of particles. And here you can see down at 73K, so down at negative 200 degrees Celsius, it's a nice tight curve. Okay, the average is there and it doesn't differ much. But as you start heating it up, you get a wider range of temperatures in the particles. Sorry, you get a wider range of particle speeds in there. So these are called Maxwell-Boltzmann distributions. I think the physics people will talk about Boltzmann stuff, and Maxwell definitely in there. But it's talking about temperature effect on the particles, okay? And so you get a range of these. Okay. So let's look at, here we've got a reaction, the same reaction, different temperature conditions, okay? So we've got the average temperature here at 300 Kelvin, and you can see the blue curve, and then we've got a 500 Kelvin, and you can see the orange curve, which is much wider. Now let's say for a successful collision to occur, you need this energy here, E, that they've marked there. Now you can see the for the cooler reaction, there's still a certain amount, I should change it to blue, of particles that are going to undergo this reaction, represented by this area here. This is kind of like a number of particles that have got enough energy to have a successful collision. So just a small amount it's going to form the products. But you can see as you widen the temperature, as you increase the temperature and widen the curve in the orange there, change it to orange, you're increasing the amount of particles that have that energy to undergo that reaction. So here you've got, I'm drawing over the blue, you've got a much larger area. So you've got a much larger amount of particles that have the energy to undergo the reaction. Okay? Oh, I said this also applies to state changes. Water evaporates at temperatures lower than its boiling point. So you get water evaporating below 100 degrees Celsius because of this curve, okay? So, because you get a small amount that's got enough energy to break away and form a gas, even though it's not at 100 degrees Celsius. This is why when you wash your clothes, you hang them out to dry, and even though it's not 100 degrees Celsius, they still dry, okay? But we also know that clothes dry quicker on a hotter day too, because more of those water molecules have enough energy to evaporate. Okay, so here I'm going to do my old models and my graphs, okay? Now you can see that I've got the same mixtures here in my models, high temperature and low temperature, and my graphs here are starting the same too. No products, which I'm going to represent in blue, and the concentration of the reactants is high, okay? So increasing the temperature of the reaction increases the proportion that will successfully collide in a shorter time and increases the rate, okay? So let's have a look at what happens. So I've started the reaction and I've got some meeting, and that's what I'm representing by the blue, these guys that have met up, okay? Now you can see in the higher temperature, how many have we got? 1, 2, 3, 4, and in the lower temperature, we've got 2 that have met, okay? So we've formed more product in the higher temperature. So I've represented that here by the concentrations going down to here and up to here, whereas in the same amount of time for the lower temperature, they've only changed a little bit. Okay, another period of time has come across. The reaction slowed down a little bit, but still the higher temperature is proceeding more. So the higher temperature, the concentrations have already kind of equaled, and then we've now got more product than reactant, haven't we? Now that hasn't happened down here in the lower one, has it? We've just got 4 of them, okay? Next step in time, the reactants are forming, but it's slowing down for both of them. Here we've got more products, but you can notice the curve here is less pronounced than the curves for the higher temperature one. Okay, and let's follow it all the way to the end. Oh, have we got an end? We've got an end there. Okay, so they're still forming the same amount. They're still forming up here and down here. We're still ending up at the same point because we had the same amount of reactants. It's just the shape of the curve. Look at the steepness. Oh, maybe I should draw it in blue. Okay, this curve versus the steepness in that curve. That one's more pronounced, isn't it? The higher temperature one. All right. Hydrogen and gaseous iodine react to form hydrogen iodine gas. Let's give a balanced formula first. So, H2 gas plus iodine gas react to form hydrogen iodide, HI. So we're going to need two of those to balance it out. If 1 mole of both hydrogen and iodine was injected at 20 degrees, produce a concentration versus time graph for this reaction. Okay? All right. I'm going to do concentration, time. Oh, let's do it seconds. We don't know how fast it is. We're making it up. But our concentration we'll do in moles per litre. I'm going to put 1 down here, 2 moles per litre, 0. Excuse me, 1, 2. I'm a bit cheaty, I know what's going to happen. Alright, I'm going to do the hydrogen in red. Going to do the iodine in green. Brain fart. And this purple colour for the hydrogen iodide. So hydrogen, 1 mole of both hydrogen and iodine. So hydrogen starts at 1 mole per litre, and it's a reactant, so it's going to decrease. But remember, the reaction starts really quick and slows down. So it's going to drop really quick and slow, and over time it's going to reach 0. Okay? Alright. So the iodine then, it also got put in at the same amount. And it's also, it's going to drop at the same rate because it's a 1-to-1 stoichiometry there. So I'm going to draw it right next to it. Let's see how I do. So they're both going to drop at the same rate, from 1, excuse me, down to 0. Okay, hydrogen iodide, there was no mention of it at the start, so it's starting at 0. Okay, if 1 mole per litre of hydrogen reacts totally with 1 mole of iodine, it's going to produce 2 moles per litre of hydrogen iodide. So at this point here in time, it's going to end up here at 2 moles per litre. Okay, so we want a curve that's going to start off quick and slow down and end up there. Okay, so it's going to start off quick, it's going to slow down and end up there. So there's my products, my hydrogen iodide products. Okay. All right. We don't know what the time is, can't predict that. We're just saying at a certain time it's going to cease. But you can see the main point that I'm looking for here is the stoichiometry, okay? As well as hydrogen and iodine being reactants, they need to decrease fast and then slow down over time and reach 0. Hydrogen iodide needs to start off at 0 and increase fast and slow down over time. And they're going to cease both at the same time, okay? And also this 1-to-2 stoichiometry. Okay. Oh, so we've got a part C. I've just kept the part A there to bring my information down. I'll copy this information down to hydrogen iodide gas. Okay, so C. So we've got 1 mole of both hydrogen and iodine injected at 200 degrees. Oh, and allowed to react. Okay, so now what we've done is we're asked for a graph, but the condition that we've changed is increased temperature. So they're both going to start and end at the same time, but it's going to be steeper. I haven't given myself much leeway with the purple, have I? Okay, so time and concentration in moles per litre. I'm still going to keep the same scale. Terrible scale. They're still going to reach the same concentrations, but they're going to reach it in a shorter amount of time. Okay? So let's say they reach it in this amount of time as opposed to that one. Okay? So the hydrogen iodide that's forming, well, let's go back to my purple, is going to reach the end here. Okay? Up here. So I need a steeper curve. Alright. Oh. Let me erase that bit. No. Oh, I'll redraw it. I need a nice steep curve. Okay. Is it any steeper? Oh. It should be steeper than that one. I should erase the first one and do it shallower. Okay. Alright. Let's do the hydrogen and the iodide. They're both starting at 1. And they're decreasing to there. Alright. How well did I do? Let's put the iodine in. I used green for iodine, didn't I? Okay, so compare it to the one above. I mean, we can extend these forever. They're not going to change. But compare it to the one above, we should have a steeper relationship. Okay, so still ending at 0 and 2. Still the same stoichiometry. It's just happening quicker, so we're getting steeper curves. Okay, let's do this part D. It was found that the rate of change for the concentration of iodine was negative 0.2 moles per litre per second at a particular moment. What was the rate of change in the concentration of hydrogen iodine at the same time? Okay, well, it's going to be a positive because it's a product. Okay, and it's going to be, we're forming 2 times that from our reaction. So it's going to be positive 2 times 0.20 mole per litre per second, which equals 0.40 moles per litre per second. All right. Increasing the concentration of the reactants will increase the rate of reaction. Okay, so we talked about temperature, now we're talking about the concentration. Okay, so we're not talking about the amount, we're talking about the smaller volume. Okay, so how I'm showing it is, here are my models. I've kept the same number of particles, I've just changed the volume. Okay, so here, have I done an animation? I have, and I'm showing the overall graph, but that's okay. Alright, so let's start down here. Okay, I'm going to start for the concentration of green and pink very high. Okay, and so the concentration in the larger volume is lower, so I'm starting lower here. The blue that I'm using to represent the products is fairly low. And so here my first period of time has gone through, and you can see that in the higher concentration a lot of reactants have met each other to form products, whereas in the low concentration one less has found it. There's more space. Okay, so think of this one is there's more likely successful collisions when you've got a smaller volume. Okay, so that top one is going faster, and you can see as we progress in time that top one it's slowing down as well, and the bottom one's slowing down. But here it's progressed much further. We're much further to the end point. Okay. And as we progress, we're producing more and more, but it's slowing down for both of them. And we end up with these 2 graphs. Okay. So notice that where they end up is different because the concentration is different, because the volume is different. Even though we have the same number of particles, the volume is different, okay? I think I've roughly done it 2 times. Okay, so halve the volume, 2 times the concentration for the top one. The reactants as well. So they start at the same concentration for the reactants, and the products ends up being the same because it's a 1-to-1 ratio here. Okay, another thing, surface area. Okay, in heterogeneous reactions, where you've got 2 different states meeting each other, the reaction happens at the interface. Or we can be fancy and say it's the phase interface because it's where the 2 phases meet each other. If the interface is a large area, there are more sites for potential successful collisions, and the reaction will happen at a faster rate. So larger surface areas have faster rates of reaction than those of smaller surface areas. Here, the diagram, okay? We've got the same amount of particles here, but here the solid is a large chunk. So I've got this surface area where the reaction can happen. Here in the smaller, in the other one, we've got smaller chunks. We've got a larger surface area for these to react at. Okay? We've got larger smaller particles, more surface area open to doing the reaction. So this one happens at a faster rate. So here graphically, we've just got something like hydrogen concentration over time. If you have large particles, you can see that we've got a less steep curve, and the smaller particles have the steeper curve. So the reaction happens at a quicker rate. Okay, another thing that can alter the rate of reaction is mixing. So trying to make sure the reaction is as homogeneous as possible and that the reactants can meet each other. Okay, so maintaining homogeneity, words. Okay, so for heterogeneous as well, it's a problem as well, because eventually the product can cloud or cover over the surface of the interface. So you want to move it away. Okay, so you want as much chance as possible that the 2 reactants are meeting each other. So more mixing, more chances of the reactants meeting each other and the product getting out of the way, the faster. So here, amount of product, the mixing is slow in the blue and faster in the red. And here you can see I pulled a graph of some kind of yield, how much product you're getting, and different mixing revolutions per minute. And you can see there's a relationship. As you increase the revolutions per minute, you increase the amount of yield in the amount of time. Okay? All right, let's do some problems. Okay, the concentration of a single product was monitored during the course of the reaction A. Okay, so reaction A in pink there. Single product, how much was formed over time? The conditions of the reaction was then changed, and we did the same thing and produced curve B. What change of conditions could have produced curve B? Okay, so curve B is less steep than curve A. It happened at a slower rate, but it formed the same number of products. Okay, so to produce curve B, a temperature increase. Well, a temperature increase will increase the rate of reaction, and we've decreased it, so no. A temperature decrease will decrease the rate of reaction, so that one looks good. Let's keep making sure. If you halve the moles of the reactants, you're going to halve the amount of product you can form. And that's down here, so you should get a curve like that, and we haven't. We've produced the same amount of product. So we haven't halved the moles of the reactants, and we haven't doubled, because then the curve would be up here. So we've just confirmed that it's the temperature decrease. Okay, we haven't altered the amount of reactants, we've just altered the temperature, so it's B. Okay, same type of thing. I think I've just copy pasted this question, but I've changed the curves here. Okay, you can see different rate and different finishing points for A and B. So what conditions could have done it? So if it was just a temperature increase, we'd get a steeper curve, but they'd meet at the same point, because you had the same amount of reactants. No. If it was a temperature decrease, they'd meet and they'd end at the same point, but you'd get a shallower graph. So no. Did we halve the number of moles of reactants from A to B? No, there's more B that formed, so we must have doubled the moles of reactants. So we had more of the reactants there, so we formed more product with B. Okay. Look at this concentration versus time graph. Okay. Which of the following is the correct equation for the reaction? So we've got A decreasing and B and C increasing. Okay. So B and C increasing and starting at 0. So B and C must be the product. Okay. So the B is wrong and D is wrong because B and C need to be the product. So we're deciding between A and C. Okay. A and B look like mirror images of each other. So they're kind of like in a 1-to-1 ratio. Okay, let's check that. In A, we've got A going to 1A going to 1B. That's all good. In C, we've got 2A going to 2B. Well, that hasn't helped us, okay? Now, B versus C, okay? There's only half the amount of C that's been produced, okay? So there must be a 1-to-2 ratio between them, just like in C here. So there's not a 1-to-1 between B and C. B and C haven't ended at the same point, so it's not A. So it must be C there. Alright, have we got another one? Alright. Oh, I've changed it up. I've added another curve in here. Which is the following correct equation for the above? Okay. First thing I noticed that A and B must be reactants because they're both decreasing. Well, that hasn't helped us because A and B. Okay, C and D must be products. Oh, that's good. We've confirmed that too because they're increasing over time. Okay, let's look at the ratios. Okay, the A graph, the green one, is like the opposite of the D graph. Okay, so A and D must be 1-to-1. Okay. A, 2A to 2D, that's all good. B, 1A to 2D, that's all good. Sorry, did I say 1A to 2D? 1A to 1D, so it's all good. C, A and D are not in the same ratio. There's 2 A's to 1 D, so get rid of that. A and D, in D, 1A to 2D, so they're not in the right ratio. So it's between A and B, okay? What we can also look at is the ratio between the products here, D and C, the blue and the pink. 2 times the amount of D was formed for every C. So it must be C plus 2D, not 2C plus D. So it must be A there. All right. I think this is the last problem, and then we'll talk about catalysts. We'll keep it all in the same video. It's a long one, but we'll deal with it. So Scott set up a series of reactions involving marble, which is calcium carbonate, and hydrochloric acid. Okay? I've got a base, carbonate, and acid, so we're going to produce salt plus water plus carbon dioxide. He deliberately changed the reaction conditions and monitored the rate at which carbon dioxide was formed. Okay? While he controlled the mass of marble chips used for each experiment, he changed the volume of the acid used, the temperature it was conducted at, and whether the marble were in chips, so large chunks, or in a fine powder, so changing the surface area conditions. What we need to do is match the reaction conditions 1 through 5 in the table. So this reaction, this, and identify it as what graph it will produce, A, B, C, or D, or E, okay? I'll just erase my scribbles there. All right. Okay, how I'm going to approach this is, okay, look at A. A is the steepest graph of all and has produced the most amount of product. So we're looking for the most amount of reactant, maybe the highest temperature, and maybe the largest surface area. So let's go down to surface area. Marble chips or powdered. Powdered will be the largest surface area, and there's only one of them. Okay? Let's just make sure it has the highest temperature. Well, it's between 20 and 40, so it has the highest temperature, and it has the highest amount of volume of acid as well, 60 compared to the other ones which are lower or the same. So this one has the most amount of product, the highest temperature, and the highest surface area. So it must be A there, the steepest one. Okay, so 5 must be A. Now look at B. B has ended with the same amount of product being formed, but just at a slower rate. Okay, so for the same amount of product to form, I'm looking for the volume of acid to be the same. So 60, number 1 here has 60. Okay, now look below. Same temperature, so it wasn't the temperature that changed the rate, but look where you got smaller surface area, we've got chips instead. So B is the same conditions, but instead of powdered, it's chips. So number 1 is B. Okay, what I might do is look at E. E has formed the least amount of product. Okay, so I need the least amount of reactant. So look at my volume of HCl. I've got 30 or 15, 2 at 30, 1 at 15. I'm guessing it's this number 4 here. Okay, all right, the chips hasn't changed, surface area hasn't changed, it's still high temperature, but we're limited to how much we can make. So E must be number 4 here. Oh, I've lost my pencil. E. Okay, 2 and 3 must be C and D. What's the difference? So C is quicker and D is slower. They've both got chips. They've both got the same amount of product, which is good because they both had it at the same point. It's only the temperature that has changed. So the shallower one must be the lower temperature, which is the 20 or the 40, so it must be the 20. So D there, the one in red, must be the lower temperature. And C must be the higher temperature. All right, so there we go, we've solved it. Let's quickly talk through what catalysts do. Or should I leave it for another video? Nah, it's only a little bit, and I haven't got any questions. Let's get it all. So we need to model what catalysts do, okay? So a catalyst, let's define it. It's a chemical species that takes part in the reaction but is not consumed. Weird, okay? It enters the reaction and exits the reaction as the same species, okay? What catalysts do is they aid the reaction in occurring at a faster rate, okay? Now, a little bit more detail there. Think about it, a catalyst as an introduction person, okay? Think about it as a person who comes along and introduces two people together. It grabs them and pulls them together. Instead of two reactants trying to meet randomly and run into each other and bouncing around in a box, imagine someone coming along and going, hey you, grabbing them by the hands and pushing them together. That's a good model for a catalyst, okay? A good simple model to start off with. So reactions with catalyst occur quicker, but it doesn't change anything else about the reaction, okay? It just speeds up the reaction. So look at our graph here. We've got a concentration versus time. Notice that the catalyzed reaction is in red and the uncatalyzed is in black. And you can see that the black is shallower than the red. So the catalyst increases the rate of reaction. Okay? Doesn't change the amount of products or reactants that are forming overall. It just increases the rate. Okay, why are catalysts used? Let's talk about that. So, industries that use gaseous reactions often use catalysts to speed up the reaction rate and produce more product in a shorter amount of time. Okay, overall in the time, if you had infinite time, they'd reach the same point. But money is time and business needs money. So you need to have, in a short amount of time, a biggest bang for your buck. So that's why companies use catalysts. Because they say, well, we've got to make this thing during a day, whereas the whole reaction would probably take a week. We want it to happen in a day, so we're going to get more product in one day if we use a catalyst, okay? So let's talk about the ammonia gas reaction. We've talked about it earlier. Nitrogen and 3 hydrogens forming ammonia. This reaction relies on many collisions in the right orientation with enough energy to overcome electron repulsion, okay? Look at it. it needs one nitrogen molecule and three hydrogen molecules to collide at the same time in the correct orientation. Four things colliding at the same time in a three-dimensional space is very, very unlikely. Okay? Two things colliding, sure. Three things colliding, chances are a little bit less. Four things colliding, what? Okay, not going to happen. Okay? So this reaction actually occurs very slowly because those likely four hitting at the same time in the correct orientation is pretty unlikely. Okay? So, let's talk a bit about my diagram here. Two molecules, if you have a one-to-one reaction of gaseous, it's likely that these two are going to collide at some time in the right orientation. If you need three of them, the likelihood is getting pretty low. So the speed of the reaction, this reaction where three molecules have to meet, is much slower than where only two. Where four need to meet at the same time, it's hugely unlikely. Okay? So looking at the stoichiometry of a gaseous or homogeneous reaction, you can kind of predict the speed, or you can contrast it with something with a different stoichiometry. Okay? So I like this. Homogeneous gaseous reactions involving more than two molecules can be a crapshoot. Okay? It's all about randomness. If only we could get the four molecules to meet each other and push them together somehow, that would speed up the reaction, and that's what a catalyst does. So when ammonia is made, a catalyst is made to speed up the reaction to make sure that the likelihood of successful collisions is increased as much as possible. Okay, a little bit more detail on how that happens. Okay, for the reaction, this one, nitrogen, hydrogen are happening in ammonia, the catalyst used in this gaseous tank is actually a solid surface of a metal, and here it's iron. And what ends up happening is the gaseous molecules hit and bond with the iron a little bit. They're trapped on a surface. It's like flies on the sticky paper, okay? They're trapped on the surface. As soon as you trap something on a two-dimensional surface, it becomes a sitting target, okay? And then collisions, the rate of successful collisions can increase because you're holding some of them still. They can't move around in three-dimensional space. You've captured them, okay? So catalyst for these gaseous reactions happens on a solid surface, and it makes them sitting targets. I like that. So that you get more successful collisions, okay, in a shorter amount of time. This is just a different diagram showing the same type of thing, where you've got a catalyst with a gas around it being trapped on the surface, and so you're getting sitting targets so the reaction can happen. All right. Okay, some other catalysts can work within, say, a solution, a water solution. And what it does is, these are called homogeneous catalysts, and these are like the matchmaker things, where they're actually moving around in three-dimensional space. They're capturing one, they're capturing the other, and then pushing them together, and then leaving. So it's there at the beginning and it's there at the end, but in the middle it's a matchmaker one, okay? So they're the like a homogeneous one. Here we call them heterogeneous catalysts because it's a solid chunk in a gaseous chamber. All right, we're going to leave it there, and there's a worksheet to do.